Topic 2.3 is structure of ionic solids. Your outcome is I can represent an ionic solid with a particulate model that is consistent with Coulomb's law and the properties of the constituent ions. So an ionic bond is formed whenever one or more electrons are transferred, forming a cation and an anion. So this is actually a Coulombic attraction that holds together an ionic solid. So it's not shared electrons, it's that attractive force between oppositely charged ions. So ionic compounds tend to be solids with very high melting points. And unlike molecules, which will form individual discrete molecules, ionic compounds exist as large 3D networks of ions. So, for example, in NaCl, the ratio is 1 to 1, so we write the formula just as NaCl. So the first question is asking, there's two different types of ions represented by the spheres. Which ones are representing sodium? So those are going to be the smaller ones that are dark gray. Those represent ions that have lost electrons, so their atomic radius should be smaller than the chloride ions, which gained electrons. So the ions formed by group 2 atoms, that's like magnesium, calcium, are almost exclusively +2 rather than +1 or +3. So explain why. So everything in group 2 has 2 valence electrons, and they obtain a complete octet by losing both of those electrons. So M+ ions are pretty unlikely. Now the third electron is going to have a much higher ionization energy. After those 2 valence electrons are removed, now we're talking about taking an electron from a lower energy level that's closer to the nucleus. So we see a big jump in the ionization energy between taking off the second and third electrons. So because that ionization energy is so high, it's unlikely that we're going to have M+3 ions. So a representative group metal, so not a transition metal, forms ionic compounds with the formulas MCl4 and MO2. So what is a possible identity for that metal? So we're looking for a metal that has a +4 charge. So something in group 14 will work, like tin or lead. Ionic compounds are brittle. Why is this in terms of like charges? So if you have an ionic compound and you hit this ionic crystal, you might force a positive charge next to a positive charge, and those are going to repel each other and it will make the crystal shatter. So they're very brittle because if you hit them with a hammer, those charges can line up and those repulsions occur. So one way that we can measure the strength of ionic bonds is to look at the melting point. So the more strongly the ions are held together, the more strong that attractive force is, the more heat I'm going to have to put in to disrupt those forces to allow it to melt. So in this table, you have some math to fill in. This force equation is a little different than the one that you saw in Unit 1, but it's the same concept, it's the same idea. So the magnitude of that attraction of that force is going to depend on the size of the charges as well as the distance between them. So don't get too hung up that this doesn't have a negative sign. This is written without the constant K. So, you can always wrap up a negative sign into a constant. But let's just focus on the size of that attractive force. So in which compound will the Coulombic force of attraction be greater between NaF and NaCl? It's going to be greater in NaF, and that's because it has that higher melting point. So because the attractive force is greater in NaF, we're going to need more energy to break apart those attractions to melt the solid. So something higher than 800, higher than 801 is what we would expect for NaF. Now looking at magnesium oxide and magnesium sulfide. So the one with the stronger attractive force is MgO, and this is because it has the highest melting point. So which of these would we predict for MgS? We're going to predict that it's going to be less energy because the attractive force is weaker in MgS. I need less energy to break apart those attractions and melt the solid. So something less than 2800 degrees Celsius would make sense. In this case, 2000. So based on the data, which factor, the size of the ions or the charge, has a greater impact on melting point? So the charge seems to be more important because the ions that are +1 and -1 have melting points around 1000 degrees Celsius, whereas the +1 minus or +2 -2 anions, those guys are going to have higher melting points around 2000 degrees Celsius. So the size of the ion also impacts the melting point, but to a lesser extent. So if we look at the fluoride ion versus the chloride ion, the fluoride ion is smaller. So that allows the ions, those charges, to be closer together, and then you have a smaller distance in the equation. So we get a bigger attraction there. So if you want to compare or predict melting points for different ionic compounds, first consider the charge of the ions. And if the ions have the same charges, then you should consider the relative sizes of the ions. So in question 9 and 10 here, we're trying to predict basically which one is going to have those stronger attractive forces. So for melting point, I would pick NaCl. They both have the same charges, +1, -1. NaBr is +1 and -1. But the chloride anion is smaller than the bromide anion. So that distance in the denominator of my equation is smaller. Between NaCl and KCl, we're again going to pick NaCl because it has one less energy level than potassium. The potassium cation is going to be larger, so a bigger distance. So the correct answer there would be NaCl. The next one is MgO and CaO. So in this case, they have the same charges again. Magnesium and calcium are both +2 and oxide is -2. But calcium is going to have a larger radius, so it's going to be a lower melting point. In the case of LiF and KBr, Li and F are both in the second row, and K and Br are both in the fourth. So the distance between those atoms, between those ions, is going to be smaller in LiF than it will be in KBr. So lattice energy is the amount of energy that we would need to separate the ions in 1 mole of an ionic compound. So these are going to follow the same trend as we would for higher melting point. So our answers are the same in question 10. So you have a couple of reflection questions here. How does the structure of an ionic solid maximize attractive forces while minimizing repulsive forces? So those cations and anions are held at a particular distance by which their potential energy well gets the deepest, like what we saw in topic 2.2. So these are arranged with opposing charges so that there's minimized repulsion between similar charges. So of these three, which would we expect to have a higher bond strength? Remember that melting point is a great measurement of that. And so between our choices here, LiCl is going to be the best choice.